All right. Well, welcome back. Today, what we're going to focus on is titrations, uh, prior knowledge that's needed in order to talk about titrations is stoichiometry from General College Chemistry 1, how to write a balanced chemical equation. In order to do a titration, you must have a balanced chemical equation of the titrant, which is what is of known concentration, and the analyte, what you're trying to find out the concentration. And so, if you don't have a balanced chemical equation, you don't know the mole to mole ratios of the titrant to the analyte. You also would like a fast reaction. If the reaction is very slow and it takes a long time for a color change to occur, you may have added too much titrant by the time, and therefore you would conclude that you have a higher concentration of analyte than you should have. So the focus today is going to be talking about the terminology, what the process looks like, hopefully helping you be able to perform a titration in the lab. And then we'll look at different scenarios of strong acid, strong base, strong acid, weak base, and strong base, weak acid. And that's where prior knowledge of doing ice tables comes in, and that's going to help us predict where the inflection point in a pH curve occurs. So we'll talk about that as well. So on this slide, what you need to focus on is what is a titration, the titrant, the substance of known concentration, and actually that's a typo on the slide. It says a solution of unknown concentration titrant. It should be known concentration titrant can be slowly added to a solution of unknown concentration from a burette. Until the reaction is complete. So the titrant is what you know, the analyte is what you're trying to find out, and the titrant is added from the burette. All right, so one of the first things we're going to look at is an acid-base titration, and we're going to assume that the titrant is a base. That's what's located in the burette of known concentration. And in the Erlenmeyer flask, we have an unknown concentration of acid. We'll also add either some water to increase the volume, or we will also add some indicator that will change color when the equivalence point is reached. So what is the equivalence point? Well, the equivalence point is where you've added just enough sodium hydroxide from the burette to equal the concentration of the hydronium ion in the acid. And so one extra drop beyond that, that drop of base has no acid to react with, or no hydronium ion to react with. So it reacts with the indicator and causes the indicator to change color. So a common acid-base indicator is phenolphthalein, especially if we're talking equivalence point of pH 7. And it's colorless in an acidic solution, but once the solution turns basic, the indicator will change pink, and that will signal for us to turn off or shut off the stopcock to prevent any more sodium hydroxide entering the Erlenmeyer flask. So equivalence point is theoretical. It is where the hydronium ion concentration of the acid equals the hydroxide ion concentration of the base. Endpoint is what signals a change and we will see a change in color of the indicator. And we hope that the indicator we choose falls around the equivalence point. And we'll talk more about that in another slide. All right, so here we have a nice diagram, a realistic diagram of titration that occurs in the lab. So again, you have the sodium hydroxide. That would be, oops, a little crazy there. I'm trying to find my point here. Yeah, so the sodium hydroxide that's in the burette, that's your titrant. And then down below in the Erlenmeyer flask is the hydronium or hydrogen ion that's in the flask. Again, we know how much sodium hydroxide is here, or what the concentration of it is. And we know how much is going to be dispensed. And as the sodium hydroxide enters the flask here, it forms water, so that's why we see water here, because hydroxide plus hydrogen ion yields water. And then what happens is once all of the hydrogen ion has been consumed, then the hydroxide ion has nothing, there's no hydrogen ion for the hydroxide to react with, so the hydroxide ion reacts with the indicator and changes the color of the substance to pink. All right, we're going to try it better on our drawings here. What's happening is I'm using a Wacom board, and it's you don't get to see what you're actually drawing. It's like drawing on a black slate, and it takes a little getting used to. I have another computer, a tablet. It's much better, but I don't have access to it right now, so that's why we're going to have some sloppy diagrams. So let's just talk about this one more time. You have the titrant, the hydroxide in the burette, known concentration, the acid in the Erlenmeyer, unknown concentration. At the beginning of the titration, it's colorless because the indicator is colorless in an acidic solution. You start adding hydroxide ion to the flask, and that converts to water. And so in this middle one, let's clean this up a little bit. Maybe we can do that, make it a little better. I feel like I'm out of practice. All right, so the hydroxide ion. Let me try something here. I got to get the hang of this. There it is. The hydroxide ion enters the flask, reacts with the hydrogen ion, and forms water. And so as long as we have hydrogen ion present, then hydroxide is going to react with hydrogen ion and form water. Once all of the hydrogen ion is used up and all we have is water molecules, then the hydroxide ion is going to react with the indicator and change to a pink color. Now, if you're doing this titration in the lab, try not to get this color. That's pretty far over. What you want is, this is not there yet, and you can see by the diagram up here that it's not there yet because there's free hydrogen ions or hydronium ions. And I see this happen a lot. Students get concerned that, oh, the titration's about to be done. Well, if you're not swirling it around, yes, you're going to have a concentration of hydroxide ion there that's going to react with the indicator. So while you're opening the stopcock, make sure you're swirling the flask so that the hydroxide ion can mix with the hydrogen ion, and so you don't get this false positive. Now, let me give you a little trick here when you do a titration. Let's say your professor says you need 3 titrations. Set up 4 or 5. Use the first one as an exploratory titration to figure out where the endpoint occurs. Like, you'll measure up here how much sodium hydroxide was dispensed, and you know the concentration, the molarity of the sodium hydroxide. So you would expect that if you have the same amount of volume or mass of acid solution at the beginning as the first flask, then you'll know about how many milliliters it's going to take for this to change color. So you can zip down to the point where you only have to add maybe 10 or 20 drops before you get to the end point. So that's what I encourage you to do. Set up more than 3 flasks. You know you're going to blow the first one. Otherwise, what I see students do is they add drop by drop here, and then they blow the end point, and they spend a lot of time on that, and then they still got to do 3 more titrations. So set up 4 or 5. Try to make them all pretty close to the same mass or the same volume. Hopefully they are if you're using a pipette. And if you do that, you'll get through the lab much quicker. I just find students get more, builds tension as this fades away, and then all of a sudden they add 3 or 4 drops, and then you get too much of this pink color too far past the end point. Another thing to remember is you can hang a drop off of the tip, and then use your squirt bottle or your water bottle, whatever you want to call it, to rinse that off. You can do a half drop, a quarter drop, and get this to be the lightest of pink. And make sure it persists for about a minute before assuming that you're at the end point. So what we know here, let me just kind of write down what's happening here. You know the molarity of the sodium hydroxide. You know the volume dispensed in milliliters. So molarity, I would just make this millimoles per milliliter. Remember, the millis can cancel out. That's moles per liter. So whatever this molarity is, if it's 0.10 molar, then you have 0.10 millimoles per milliliter. Multiply that by the volume dispensed in milliliters, and that will give you the moles of sodium hydroxide, or in this case what we're really interested in is the hydroxide ion dispensed. Now, you know that here's your balanced chemical equation. Sodium hydroxide reacts with hydrochloric acid. And again, you should know that anytime you add a strong base to a strong acid, the 2 products you get are a salt, and you also get water. All right. So this equation's balanced. So what we see is it's a 1-to-1 relationship, mole-to-mole relationship between the hydroxide ion and the hydrogen ion. And therefore, whatever the moles of hydroxide dispensed, that is the moles of the hydrogen ion. So if you know what the moles of the hydrogen ion are, then you can divide by the volume of acid that you placed in the flask, and then you can get the concentration, the initial concentration of the acid solution. So that's what you're going to be doing. And this is the simplest case scenario where you have a strong acid with a strong base, called the neutralization reaction. And with the neutralization action, you always get salt and water. All right, so another thing you'll probably be doing in the lab is making a titration curve. So when you make a titration curve, the thing you want to focus on initially is to have a title. You will have the y-axis and you'll have the x-axis. Make sure you label those things. It's very important. I know a lot of people forget, or they assume that people can do this, and I do see sometimes some mislabel, but you should label it. You should label what it is. Now, I would say sodium hydroxide and hydrochloric acid, and maybe I would, I would probably go on and label what that is. But what the reason why they say strong acid and strong base here, it doesn't matter what strong acid and strong base are if they're monoprotic, and a monoprotic acid and a monoprotic acid. What you're going to have is you're going to have the equivalence point will occur at a pH of 7. And you go, why is it a pH of 7? Well, again, if you take the sodium hydroxide and you react that with the hydrochloric acid, you're going to get water, which is a pH of 7, and sodium chloride. And this is the part that you have to know from prior knowledge, and that is sodium chloride is a neutral salt. The sodium ion does not undergo hydrolysis with water. And what I mean by that is that the sodium ion does not react with water and form sodium hydroxide plus hydrogen ion. That does not happen. So sodium ions do not change the pH of the solution. And the same thing about the chloride ion. The chloride ion does not undergo hydrolysis with water and form hydrochloric acid plus the hydroxide ion. That does not happen. So that's a neutral salt. And again, if you don't remember that, you need to go back to the previous chapter and look at how salts affect pH. All right, so this is a neutral salt. If you have an acidic salt, you say, what's an acidic salt? Well, how about ammonium nitrate? All right, so here's your fertilizer, ammonium nitrate. So ammonium nitrate, when it dissolves in water, we get the ammonium ion, and we get the nitrate ion. And you should recognize that the nitrate ion is the conjugate base of a strong acid, nitric acid. So this part's neutral, does not affect pH. But the ammonium ion will react with water, and we will form the hydronium ion plus ammonia. And since we generated the hydronium ion, we're going to have the properties of an acid, and the pH is going to be less than 7, and it's going to be an acidic solution. All right, for a basic salt, that would be like sodium fluoride. So sodium fluoride, again, sodium ion does not react with water, but the fluoride ion will react with water because it's the conjugate base of a weak acid, hydrofluoric acid. So we're going to form the molecular acid plus the hydroxide ion. So because we generated the hydroxide ion, the pH is going to be greater than 7, and we're going to have a basic solution. So this is an important bullet point because we're going to be looking at different scenarios where we have strong acid with strong base, we get a neutral salt formed. We're going to have a strong base with a weak acid, and we're going to have a strong acid with a weak base. So this is what the curve looks like. It starts out, the pH doesn't change that drastically because you have an excess of acid in the flask. And then all of a sudden, you've added just enough hydroxide ion to consume all of the hydrogen ion. And so any extra hydroxide added is going to cause the pH to jump dramatically. And then we get a leveling off effect here of excess hydroxide ion. All right. So that's what we're looking for when we're doing a pH titration. All right, some other components that are important to look at here. So the initial pH is that of the weak acid solution. Oops, let's go back. So the initial pH of a weak acid solution. All right, so what we're looking at here is a weak acid solution. Here's the initial pH. Yeah, it's lower than 7. It's acidic solution. Okay, so if you wanted the general equation here, you have a weak acid. You're going to add a strong base. We'll just write the hydroxide ion. Sodium hydroxide, potassium hydroxide, lithium hydroxide. And we're going to get water. The hydrogen ion from the weak acid reacts with the hydroxide ion, forms water, and then we get the conjugate base, A negative. Well, A negative is the conjugate base of a weak acid, so yes, that's going to react with water. It undergoes hydrolysis, and we get HA plus the hydroxide ion generated. And so that's why you see the equivalence point here is above pH 7. All right? So what you need to focus on is when you're titrating a weak acid with a strong base, you will have an equivalence point that is above pH 7, and the reason is spelled out here. All right? Now, when does the pH equal the pKa, and why do I care? Because when the pH equals the pKa, that's halfway to the equivalence point. Halfway. So here's the equivalence point. If we work this backwards, so we've added 25 milliliters and we're at the equivalence point. So at 12.5 milliliters, we are in the range where pH equals pKa. And you notice that kind of looks like the Henderson-Hasselbalch. We have plus the log of the conjugate base concentration over the acid. So that's why that's important. These are both the same concentration. These are both the same concentration, so we get the log of 1 and the pH equals the pKa. That's an important point. Halfway, find out where the equivalence point is and work your way backwards to the halfway point, and that's where you'll notice that the pH equals the pKa. So again, Henderson-Hasselbalch important. If you don't understand that, I mean, I could make another video. I could make a video on that, but in order for you to understand a titration and some of the points on the titration, it's important that you can use the Henderson-Hasselbalch equation as well. All right, let's look at this problem. This is kind of a strange problem, but let's just look at it anyway. So what we have here is we have a burette. Draw you a picture. Make sure you do that. And if you don't like drawing a conical flask, just put your receiving vessel like that. And so what we know is, which makes this one a little strange, is we know the volume of sodium hydroxide in our analyte container. And we know the concentration of the sodium hydroxide is 0.200 molar sodium hydroxide. And so up here as our titrant, we have the nitric acid. And we know that the concentration is 0.200 molar. So the question is, they want you to calculate the pH at various points. And so the first point is after you've added 30 milliliters of nitric acid. Now, this problem is kind of contrived in that, notice both of these have the same concentration. So in order for you to reach the equivalence point, you'd have to add 50 milliliters of this nitric acid, since the reaction is nitric acid reacts with sodium hydroxide to form the neutral salt sodium nitrate plus water. So it's all 1 to 1 to 1. So with the addition of 30 milliliters of nitric acid, we know that we haven't consumed all the sodium hydroxide. So the first thing we want to do is calculate the concentration of the sodium hydroxide. So let's do that. So Again, you need to decide whether you want to work in the realm of millimoles and milliliters, or do you want to work with liters, and you have to make that decision. So they converted the 50 milliliters into liters. They multiplied by the concentration of the sodium hydroxide. This is how many moles of sodium hydroxide that is in this container here. And so then they know that they've added 30 milliliters of 0.2 molar nitric acid, and this is how many moles of nitric acid that they've added. So this is not an ice table. This is a stoichiometry table. So a stoichiometry table, what is the active reaction here? What is the net ionic reaction? Well, it's the hydroxide ion of the sodium hydroxide reacting with the hydronium ion of the nitric acid to form water. So our initial concentrations of the hydroxide ion has been calculated to be number of moles is 0.01 moles of hydrogen ion or hydroxide ion, and 0.0006 moles of nitric acid is added. So initially we approximate this to be 0. Remember, it's not actually 0, it's 1 times 10 to the negative 7th molar, but these number of moles are so large compared to 1 times 10 to the negative 7th molar that we're going to approximate that the original concentration of the hydronium ion is 0. So after we add this nitric acid, all that hydronium ion is going to be consumed by this larger quantity of hydroxide ion. So in the end, this is how much hydroxide ion is left over, and all of the hydronium ion has been consumed. So the next part is to determine the pH of our new solution. Well, we know it's basic because we do have moles of hydroxide ion, but we do not have moles of hydronium ion. So let's move to the next slide. So we take the moles of hydroxide ion left over, and we divide by the 50 milliliters, which is 0.05 liters of hydroxide ion we had in the reaction container, plus the 30 milliliters of nitric acid that we add. So the volume has changed here. The total volume has changed, and that's the most common mistake in this problem. This is what students miss the most right here. So if we take the moles of hydroxide divided by the total volume, we get 0.0500 molar. We take the negative log of that, and that doesn't give us the pH, it gives us the pOH. So this is the pOH, and to get the pH, we say 14 minus the pOH, and we get a pH of 12.7. Yes, it's basic, and we would expect it to be basic since we have extra hydroxide ion in the solution. All right, at the equivalence point, that's a quick answer, right? At the equivalence point, all of the nitric acid has been consumed. Let's look at it again. Sodium hydroxide reacts with nitric acid to form water plus the neutral salt sodium nitrate. So all the acid and base are consumed. We have water and a neutral salt, and therefore the pH is 7. So you don't have to calculate that. Just make sure that anytime you see the titration of a strong base with a strong acid or vice versa, that you should always have the equivalence point at a pH of 7. All right, that's where we're going to stop this video. I know it's a lot of talking. I will try as we go through the semester to get these videos down to about 10-minute snaps, and then we'll add a few of them together. But nobody wants to listen to me talk for 30 minutes online. So I'll put this video together, and they'll be posted on my Professor Chemistry YouTube channel. And I would tell you to go on and subscribe to Professor Chemistry, the YouTube channel, so that anytime I make a new post, you'll get a notification that a new post has been made. Again, if you have any questions, you'd like to see something different, you have a question on a particular problem, we can work those out. It just gives me, the whole thing is that there's going to be a time lag there. And so try to stay ahead of the curve and read a little bit ahead and try some of the problems so that you can ask questions and I can get back with you before something's due. So it's kind of like, the Mars rover, it takes 8 minutes or something like that for each communication. So there's going to be a lag in communication between you, me, and then using this program. So I hope that helps, and I'll develop another video shortly. Thank you.